I'm here to talk about water supply to standpipes, and specifically to buildings with fire pumps. Now, I'm coming to you with this information because my agency, I asked the question, how are we supposed to supply water to standpipes, especially those with fire pumps? And the answers I got back weren't very good. We really didn't have a good idea of how we were supposed to work with these building systems to make sure the right water supply was making it up to the fire floor. So it took a lot of research on our part. We came up with some answers, and that's what I'm here to talk to you today about. But first, before we jump into it, I want to assure you, all of us here, we're going to fight some fire today, all right? Over here, we got our engine companies. Over here are our truck companies. And these eager beavers here in the middle have all been promoted to battalion chiefs. And their job is, like we know, it's just to remind us, put water on the fire. So thanks a lot. Really appreciate it. So I'm going to make 3 assumptions about everybody in this room when they see this picture right here. All of us want to be at this fire. All of us want to be first due to this fire. We're here on our off day trying to make ourselves better at our profession. We're professionals. We're good. We want to be here first due. The second assumption is some of you are probably sitting here going, hey, Chris, there's a fire pump in this building. What's the big deal? There's going to be water. And that's a fair question. We'll talk about that. And then some of you are probably saying, I don't have buildings like this in my agency's jurisdiction. And that's understandable. But what I'm going to offer is that while we're going to talk about standpipes and water supply in the vertical environment, in high rises, I bet you in your agencies you have commercial warehouses, large manufacturing facilities, and other buildings that have standpipes and that do have fire pumps. And so these concepts we're going to talk about do apply in those buildings as well. All right, so I said we're going to fight some fire. And for the truckies in the room, engines over here, truck companies here, battalion chiefs in the middle.
Fire dispatch calling box 0130. Report of smoke and flames seen from the top of the building. Caller says looks like the building's on fire. 522 Southwest 5th Avenue, the Yeon building. So be for Heavy Squad 24, Engine 1, Engine 4, Engine 3, Engine 21, Engine 13, Engine 15, Engine 16, Truck 1, Truck 4, Squad 1, C4, and C1. Fire map page 5394, C Charlie, respond on Ops 3, time of dispatch 2350.
All right. So all of us, we probably heard that, and we all got a little excited. That sounds like fun. And I know some of you aren't thinking, oh my gosh, that's a lot of resources. Forget that your agency. Today we're one fire department. We got all the resources we need. We're going to talk about it in that fashion. So here's our hypothetical building fire. 23-story condo, residential condos. Got a fire mid-story in the building, and it's a combination sprinkler standpipe system with a fire pump. So before we all can jump off our rigs and go forth and do good work, we got to talk a little bit about what a standpipe, what are the components of a standpipe, and I want to talk to you about this really key concept called system demand pressure. So every high-rise or every building with a standpipe, they're often going to start with a fire pump on the main floor or the floor just in the basement. They're going to be supplied by the water main, the city water main, or an on-site water source. It's going to have a standpipe riser going up through a stairwell. It's going to have pressure-reducing devices at certain floors, certain amount of the lower floors. And it's going to have an FDC connection with a check valve that connects to the standpipe on the downstream side of the fire pump. So this concept of system demand pressure, it comes from NFPA 14, which is the standard that governs standpipe systems. Now, if you're like me, when I think of NFPA standards, it makes me a little queasy, makes me want to vomit. They're not fun. They're not fun to look at and read. But if you get into it and you spend the time getting into it, you can learn a lot about these systems. And that's where our research really was focused to begin with. System demand pressure is a big, long definition. and all I'm going to say about it, I'm going to summarize it for you, is it's a unique pressure that is specific to every different building with standpipe systems and fire pumps. And you can think of it like, remember when we were back in recruit school and we were learning about pump discharge pressures and how to set the pump for a really complicated hose lay. You had lines that went out and it wide off to other lines, and you had a fog nozzle over here at a certain GPM and a smooth bore over at a different GPM, and you had to figure out what's the pump discharge pressure for the engine for this hose lay. System demand pressure is basically the same thing for a standpipe, because NFPA 14 says that the most remote outlet in the building, which is often in a high-rise would be the roof outlet, has to have 65 or 100 PSI at the outlet, depending on when it is built. So that's kind of like that pump discharge pressure diagram we're trying to figure out in recruit school, that final nozzle. There's one pressure that comes out of that fire pump that's going to supply the entire building system and get 65 or 100 PSI at the most remote outlet. So that system demand pressure is the key piece of information that, should we have to supply water into the FTC, that's what's going to get water out of any outlet that we need in the building. And this was a big new idea for us. We'd never really spent time looking at NFPA, looking at the documents, and understanding this concept. Pressure reducing valves are kind of a key component in here because they regulate the pressure on the lower floors where pressure is going to be too much. 175 is the most pressure that is going to be allowed out of an outlet. And those regulating devices go in there, and what they do is they're set based on the height in the building, and they are set based on the system demand pressure. It has to have that demand pressure in it to get the correct amount of pressure on the outside, out of the outlet, to the firefighter. So that makes system demand pressure and that idea of understanding that for every building very important. All right, so we got our box assignment. You heard it tapped out. Our first truck over here is going to arrive. It's going to go to the fire floor, force entry, start doing a search, locate the fire. Our first engine's going to come in. We're going to connect to the floor below, stretch a line up onto the fire floor. A second truck's going to come in. They're going to go to the floor above, help with search, look for extension. Second engine is going to come in and help get that first line in service. That's all their job is to do. Engines 3 and 4 are going to come in. They're going to set up for water supply to the FTC should we need it. Squad 1 arrives. They're lobby controlled. They're in charge of all the building systems and controlling the elevators. Engines 5 and 6 are going to search the stairwells all the way to the top, looking for anyone who's gone to the stairwell and for some reason has gone up. Engine 7 comes in, and they're RIT. And remember our chiefs? They're here, they arrived, and they're just going to remind us to put water on the fire. We really appreciate your help. Thank you. So here we are. We got water. We're going on the fire. So let's talk about some of the misunderstandings my agency had. First is, we thought that our job is to arrive on scene, connect to the FTC, and start putting water into the system to assist the working building fire pump, because we didn't understand, we didn't think there'd be enough water coming in through the standpipe to supply our hose lines. In reality, NFPA 14 mandates that if there's one standpipe coming up, there's going to be 500 GPM flowing out of that first standpipe. So that's effectively kind of 2.5s going. And if there's an additional stairwell with a standpipe, that's another 250, and another 250 on a third stairwell. It's not all the water in the world, but it's a lot more water than we expected. So that was one thing that kind of we learned after our research. Number 2, we thought, okay, if we're going to come in and assist this fire pump, we're going to do great work, because we're going to connect to the FTC and we're going to pump 150 PSI into the FTC, and we're going to help out the system and assist and provide all this great working pressure and flow. Well, in our building, which is 23 floors, the system demand pressure is roughly 230 PSI from the fire pump. And with that check valve there on the downstream side of the fire pump, that check valve is there to prevent the pressure from the fire pump going out the FTC. So if we put 150 PSI into the FTC against 230, are we going to move any water through that check valve and into the system? No, we're not moving anything. So that was another one of our misunderstandings where we're not doing a thing by putting 150 PSI into the system. Our third misunderstanding was if we did decide, okay, we're going to take over water supply, forget the fire pump, we're going to do exactly what we want to do, provide water, go fight that fire. We thought the driver of the water supply engine, they just need to calculate their pump discharge pressure based on the fire floor. But if we go back and think about system demand pressure and those pressure reducing devices, that system needs the pressure that is required to get 65 or 100 PSI to the most remote outlet, the top floor. So if we only calculate to the fire floor, we're not putting the necessary pressure in, which means we're not going to get the pressure out of the outlets we're expecting or the flow. So that's the third kind of misunderstanding we just missed the boat on. And it took a lot of research and a lot of reading at NFPA documents, which no one likes, but we came up with some really good stuff. So here we are. Let's talk about it. We're back at our fire. Our engine companies, we got two drivers that are working on getting us water supply. But remember, we talked about some group in here, they were thinking, hey, there's a fire pump. What's the big deal? Why do we need water? We got all the water we can need. Here's the thing is, we're eventually going to probably need to provide water into this system because in combination systems, the fire pump is supplying both the sprinklers and the standpipe. But NFPA 14 says that the fire pump will only supply the flow and the pressure for the greater demand of the two. And depending on how much fire and how many sprinkler heads are going off, that will most likely be the outlet. So then your flow is diminished to your sprinkler system. And if you research a lot of high-rise fires, like the One Meridian Plaza fire, the fires that big high-rise fires that they've had in LA, eventually it's sprinkler systems that comes together and puts the fire out. So we'll need those sprinkler systems functioning. So we're going to need to take over the system and help get those back online and flowing along with our standpipe outlets. The center picture, that's a picture, obviously, of a standpipe riser. It's looking down the riser. And from a wet system where the water stood in the system for years. The industry, fire protection engineers, they expect, this is a piece of data that I thought was interesting, from 600 feet of Schedule 10 piping, they expect 100 cubic feet of material to degrade from that wall. That's a lot of material that you can see just sitting there degraded, and once water starts flowing through that system, it's going to break off and start flowing through the system to the sprinkler heads, to your nozzles. It's going to cause some loss of flow. So we're going to want to help regain that flow. And lastly, that photo came from a guy that I follow on Facebook. His agency did some hands-on training one day with a standpipe, and that pop can came through their standpipe. So there is a very real possibility of a loss of flow through our system, and we're going to want to take over the water supply duties and help out. All right. So back at our fire, we decided, okay, we're going to need to take over the water supply role, and how do we do that? How do we figure that out? How does the driver of the water supply engines, one of my drivers from over here, how do they figure out that system demand pressure, that unique pressure we need to know for this building? Well, we borrowed an idea from FDNY, and we created this is a pump card right here. And basically, we averaged the building heights, the floor heights of all our buildings, the amount of pressure-reducing devices that might be in systems, and the drivers, instead of, one of our misunderstandings was calculating from the fire floor, they stand on the curb and they count the number of floors in the entire building. And then on the upper left side, they look at the floor and they go over, and that gives them a ballpark system demand pressure. Some pressure that they can at least get past that check valve and start positively affecting the water flow through into the system. So that's one way. But here's another thing that we realized when we researched NFPA 14. NFPA 14 actually says put the system demand pressure at the FDC. It's actually in the NFPA standard. And the thing with standards is your agency, your fire marshal's office, your city, you choose to adopt these standards as your fire code. We never saw this, so we never put it into our fire code, and none of our buildings have this at the FTC. Isn't that the easiest way, engine drivers over here? If you pull up and you connect, it'd be a lot easier to just look at the FTC and say, hey, look, for this, I have to put 225 PSI into the system. We missed that, so now we're having to go back through and try and convince buildings to add such signage to their building. And some fancy buildings, they don't like to add signage because they think it mucks it up. So that's an interesting part that we figured out in our research. All right, so we put water in the system, our engine over here, we put the water on the fire. Thanks, Chief, for reminding us how to do that. Trucks were helping us check for extension. We got our fire out. Hopefully you see the importance of system demand pressure. What I've given you today is really just an introduction to the concept. There's a lot of information out there in some articles in the industry. I definitely encourage you, despite how much you probably feel how uncomfortable it is to read those standards, I encourage you to read NFPA 14 and learn some more about the system and the standard. I hope you saw that it can apply not just in the vertical environment, but in the horizontal environment as well, for those large warehouses and manufacturing facilities that you might have in your agency. And there's really only one fire that I can think of where this system, this concept may not apply, but we can talk about this fire in the hospitality suite at the end of the day today. Thank you for your time. I hope the information was useful. Have a good one.